Hello. In this section, what we're going to look at is what the graphs of quadratic functions and equations look like. In the earlier part of this unit, we looked at like our toolbox tools. How do you add, subtract, multiply, and divide them? By divide them, we meant factor them. So how do you work with them at like an arithmetic level? And now we're going to start to look at what do these graphs of these relationships look like. So the graphs of quadratics, they look something like these. We're going to learn that these shapes are called parabolas. Why do people study them? They study them for a variety of reasons. They tend to mimic cost and profit equations. So as people demand more, the value of something's going to increase. But if you make too many of them, then the value of that thing's going to decrease. So there's some point in the middle, which is like a best case scenario. The main reason why people ever began to study them was because it turns out that the path of anything that moves through the air in a gravitational field, and well, on Earth we experience gravity, it follows this parabola shape. And this parabola shape can be modeled by a quadratic equation. And so people studied it because if you understood the quadratic equation, you could determine how high things went or how far they're going to go. So you can predict something even before it happened. And that seemed pretty powerful back when they first discovered it. So that's why we study quadratic equations. There's a variety of reasons. To start, we're going to look at the most basic one. So a quadratic equation, we're going to define a quadratic function here in a little bit. It's the same as a quadratic equation because these are functions. It's anything where the biggest power essentially is going to be a 2. And that's a quadratic equation. The general form for it looks like this: ax squared plus bx plus c. It's an extension of, well, lines. Well, lines were just mx plus b, so it would just be like this part right here. Now we're adding a higher power to it, and that's what makes it be a quadratic. The reason that it's called quadratic, that might seem strange because, quad means 4, is because the Greeks were the first to kind of work with these, and then the Greeks were always interested in the most perfect of something, and the most perfect quadrilateral, the most perfect 4-sided figure is a square, and so that's where they called these squaring functions. It's kind of where we get the roots for these ideas. So the parent function, the most basic type of quadratic function that we could study would just be y equals x squared. The b and the c are 0 and a is 1. And so to get an idea of what this looks like, you start by making a table. It's what you do when any type of new function that you get, you just start by making a table. So we're going to go from -3 to +3. We get to pick our x's and just plug values in. Let's start with 3. If I put 3 in there, 3 squared is 9. Just putting 3 in for x. 2 squared is 4. 1 squared is 1. 0 squared is 0. Then I put the negatives in. -1 squared, if you don't know, in the calculator, you need to put parentheses around the negative numbers. Otherwise, if you don't, it will not give you the correct answer because it's going to do the squaring first and then multiply by the -1. Because you should know that a negative times a negative is going to be a positive. That's why this answer should be a +1. And then you'll realize there's actually some symmetry. It just repeats itself. These graphs are symmetric because they're U-shaped figures. The right and the left are mirror images of one another. If I go plotting these points, 3, 9 right here, 2 squared is 4, 1 squared is 1, 0 squared is 0, and then here's the right side. And then the left side is just a mirror image of the right side. And you could keep going up and up. Obviously, 4 squared would be 16, 5 squared would be 25. You see that these things grow quicker over time because when you square a number, it gets bigger than it had been before. So they're not going to be straight on each side. They're curved. And that's what the parent function looks like. What we're going to do in the rest of this investigation is look at what roles A and C are going to play in altering the equation. Before we do so, we need a few vocab. I kind of already previewed this. We're studying quadratic functions or quadratic equations because these equations are functions. Every input x only has one output y. A quadratic function is a nonlinear. Why do they say nonlinear? Because these do not make lines. Function that can be written in the form y equals ax squared plus bx plus c, where a cannot be 0. If a was 0, this part would disappear. It would make a line, and therefore it wouldn't be a quadratic. So you need to have a squared term. There needs to be a power of 2 in the equation, and the biggest power, the degree, needs to be a 2. You can't have a power bigger than a 2. The shape that a quadratic function makes when you graph it, we call a parabola. That U-shaped graph that you get when you graph a quadratic function, we call a parabola. It comes from the root words para, meaning with, And then bowl, obviously meaning like a bowl with curvature. So it's a graph with curvature. That's where we get parabola, with curvature. When you graph a quadratic, it'll look something like so. There's some key parts of the graph that we should point out because we're going to use these terms. The vertex is the point of change. If the graph opens up, the vertex will be the lowest point. If the graph was opening downward, like if you toss something in the air and it comes back down, the vertex would be the highest point. So the vertex is either the lowest point for a graph that opens up or the highest point for a graph that opens down. You can also define it as the point of change, where the graph either goes from down to up or up to down. The other vocab word that goes along with quadratics is the axis of symmetry. It's shown in blue right here. Really, it should be, is this going to allow me to do it? It should be more of a dashed line. It's not an actual part of the graph. It's an imaginary line that we know is there. It's the line where our graph is symmetric about. It's where if I could fold this as a piece of paper, that's the line I'd have to fold along so that the right side would match up with the left side. So it's where our mirror would be located if it was going to be a mirror image. So that axis of symmetry is the imaginary line that passes through the vertex and divides our parabola into two symmetric halves. It's where the middle of our graph is. As always, our domain is the set of all x values for points that occur on my parabola. For parabolas, it's always going to be all real numbers because these graphs go all the way to the left and all the way to the right. My range is the set of all possible y values, and that will not be all real numbers because these graphs either are going up or down, so there's going to be some values of y that it will not get. We'll deal with specific cases when we get to them, but just recall, domain and range is what they've always been. Domain is the set of all possible x values that occur on the graph, and the range is a set of all possible y values that occur on the graph. Our graphs are parabolas in this case. So what we're going to do is we're going to look at, we know what the parent function looks like. I've sketched it here in blue, the first one that we did, just so we have a reference. We're going to see what ways A and C alter the original equation. What roles do those play? So A, let's say I make A bigger. A originally was a 1 because it was y equals x squared, so 1x squared. What if I make it a 2? What will that do to the graph? So I just make a table to see before I understand more about what's going on here. I just plug points in, put 3 in for x. You need to do order of operations, square before multiply, PEMDAS. 3 squared is 9, then I multiply it by 2, I get 18. If I put 2 in there for x, 2 squared is 4, and then 2 times 4 is 8. I put 1 in there, 1 squared is 1, 1 times 2 is 2, 0 in there, 0 squared is 0, times 2 is 0. Then it's just going to be a mirror image, 2, 8, 18. If I plot the points, 0, 0, 1, 2, 2, 8, I have the right side, then I sketch the left side. And what I should be noticing is this graph is a little thinner. It's a little steeper. The reason why is because I've multiplied by 2. It's kind of like a slope. It is not a slope, though, because slope is only for lines. So I kind of tend to call this like the steepness factor. When our steepness factor gets larger and bigger than 1, it's going to make our graph steeper because I'm multiplying by a number bigger than 1. It makes it thinner. So that's what happens if we multiply by a number bigger than 1. What happens if I multiply by a number less than 1, like a half? Well, plug points into C. Put 3 in there. 3 squared is 9. Half of 9 is 4.5. Put 2 in there. 2 squared is 4. Half of 4 is 2. 1 in there. 1 squared is 1. Half of 1 is 0.5. Put 0 in there, I get 0. Then it's just a mirror image, so these numbers repeat again. And then plot. 3, 4.5, that'll be right there. 2, 2, 1, 0.5, 0, 0, and then the graph will look like that. Over here, mirror image. And what you should notice is it's wider. The blue one is now steeper than the red, which means the red is less steep. Another way of saying less steep is this is going to be wider. This one up here was steeper. So we see if the number that I'm multiplying by is less than 1, it's going to make the graph wider. What do you think would happen for the following? 5, 8, or 50? Well, I can play around with this in Desmos. C. So parent function right there in purple. If I make A be 5, steeper. What if A is 8? Even steeper. What if it's 50? Very steep. So as the number gets bigger, it affects the steepness. Now, watch what happens. Let's do 0. Go 5.1. So this will be a nice little video. So, right, as A gets bigger than 1, gets steeper. As it gets smaller, it gets less steep. And then right as it's less than 1, this is where it's going to be wider. So anything in between 0 and 1, it's going to be wider. Once it gets to 0, it's going to go completely flat because it disappears and makes a line. But anything between 0 and 1 is going to be wider. So that's the role that A plays. A affects the steepness. So A is our steepness factor. In summary, as A increases, is bigger than 1, our graph gets narrower, gets steeper. As A decreases in between 0 and 1, the graph is shrunk vertically, it gets wider. So that's the role that A plays. A affects the steepness. Now let's see what C does. So we're going to set A back to 1. In science, they would say that's going to be a control now, and we're going to affect C. We're going to add or subtract. So we started with A. A is the multiply factor. Now we're going to add or subtract and see what that does to the graph. What if I add by 3? So we just plug numbers in. 3 squared is 9. Add 3 is 12. 2 squared is 4, add 3 is 7, 1 squared is 1, add 3 is 4, 0 squared is 0, add 3 is 0, then it's a mirror image. Plot my points. Hey, it doesn't start at 0, 0 anymore, it's moved up 3. 1, 4, 2, 7, 3, 12 doesn't fit, but I can imagine be somewhere up here. And then I just mirror image. That there, somewhere there, and it looks like that. Well, what did it do to the graph? You can really see based on the vertex. The vertex moved up 3. All points actually got moved up 3. Like look at this point, up 3. This point, up 3. It actually is no steeper than the original. If I could move this down, you'd see it's actually the exact same steepness. So don't let that little illusion fool you. It's actually the exact same steepness because they both have a 1 out front. So what did this do to the graph? This moved it up 3. So adding moved it up 3. Whereas the multiply out front made it steeper or wider, depending on if it was bigger or less than 1. What if I subtract? You probably have an intuition about what it's going to do, but let's check. Put 3 in there. 3 squared is 9. 9 minus 4 is 5. 2 in there. 2 squared is 4. 4 minus 4 is 0. Put 1 in there. 1 squared is 1. 1 minus 4 is negative 3. 0 squared is 0. Minus 4 is negative 4. And then it's just a mirror image, so I can recopy in the reverse order and plot my points. So what? 0, negative 4. So I see actually this vertex moved down 4. 1, negative 3. 2, 0. 3, 5. And then just mirror image. And if I graph it, I see that's what it looks like. You can really track with the vertex. The vertex moved down 4. Well, actually, all points moved down 4. This one moved down 4. This one moved down 4. All points moved down 4. And don't be tempted to say just because the blue is inside the red that it's necessarily narrower. They're actually the exact same steepness. It's just it got moved down 4. So what's the role that C plays? Well, you can see, so this one plus 9, that should move it up 9. That should move it up 15. And this should move it down 7. Let's check in Desmos to see. There's our parent function. First one, there's the plus 9, moved it up 9. The plus 15 moves the whole graph up 15. The minus 7 moves the graph down 7. And if I type in a parent function, y equals x squared, and then I let C play, as I can see, as C is positive, moves it up. When C goes negative, it moves the graph down. So that's the role that C plays. C moves the graph up and down. It's the exact same steepness. You can see exact same steepness, it just moves the graph up and down as long as the A is 1 still. So what role does C play? C moves the graph up and down. If C is positive, the graph moves up. If C is negative, the graph moves down. And here's a little summary table of everything we just said. So as we said before, A is our steepness factor. If A is bigger than 1, it makes it steeper. If A is in between 0 and 1, it makes it flatter. I don't believe we looked at what happens if A goes negative, so let me show you that. If I let this video play, so there's A getting bigger, steeper. There's A getting smaller, right? If it's less than 1, it gets flatter. But what happens when A gets negative? That's what's going to make graphs open upside down. So if A is negative, it'll open upside down. If the number is a number negative and bigger than -1, what I mean by bigger, if its absolute value is bigger than 1, it'll be steeper. If it's a negative number in between -1 and 0, then it'll open up wider. It'll just be open upside down. So negative just opens it upside down. The absolute value of the number still tells you if it's steeper or wider. Steeper if the absolute value is bigger than 1, wider if the absolute value is in between 0 and 1. And the last part, C moves the graph up and down. If C is positive, it's up. If C is negative, it moves the graph down. So this is just a nice little summary table. I'm going to ask you to try, just in words, summarizing what we kind of discovered today. Zoom out a little bit. That's a little too much. There we go. In words, I'd like you to describe how these graphs would compare to the parent function y equals x squared. So here's your vocab table. Your vocab table is words like you can say the graph gets moved up, down. What else can you say? You can say that it's steeper. You can say it's wider. And then the very last word that we can use today is that it opens upside down. So you have 5 words that you could choose from. You should say by how much. So like if it's moving up, you should say up how much. Up 10, up 2, whatever. If it's moving down, say down how much. If it's steeper or wider, you can just say steeper or wider. So just describe in words how the graph of these would compare to the parent function. So pause the video now, unpause it once you've tried and want to see how it's done. Okay, let's go through it. So just going down the line here, what is this 3 going to do? Well, the 3 is a number bigger than 1, so that's going to make it steeper. The negative will make it open upside down, and the +5 will make it move up 5. So this red one, you can say, is narrower because it's 3. It's opening upside down because of the negative, and it got moved up 5. The second one, which I've done in green, is wider because you're multiplying by a number in between 0 and 1, less steep, and it got moved up 3. So your words you'd be saying here are wider and up 3. So just to show an example for this last one, this is what you should say. You would just say, you can even use bullet points. Wider, up 3. And that's it for today. When you're graphing, I would highly recommend that you make a table to track your points. It's much, much easier if you make a table. You can be much more exact. So that is it. Thank you very much and have a good day.